This is version 2 of this video because I sounded so bored the first time that I've decided to re-record it. And as an Easter egg, I'll give you the answer to this joke. It's the rudest joke you can tell middle school and not get in trouble. What's the difference between a snowman and a snowwoman? Answer at the end. All right, why are some reactions of alkenes classified as reduction while others are classified as electrophilic addition reactions? Well, let's find out. So if it's reduction, the oxidation state goes down. That makes sense. That's what the word means. You could be adding hydrogen or you could be removing oxygen. Whereas for electrophilic addition, that's where you have an electrophile, something that's positive, and it's attracted to those 4 electrons there in the pi and the sigma bond in the alkene. Alrighty, so let's look at hydrogenation first of all. Let's see about the oxidation states. Hydrogen is +1 in a compound, which means that carbon's -2. And over here, by the same logic, that's +1, +1, +1. So that's going to give me -3. Okay. So oxidation state of carbon has gone from -2 to -3. Yep, that's good. I've gained hydrogen. I haven't lost oxygen though. So that's looking good for the reduction. So what about this electrophilic addition? Is there an electrophile? Well, actually, this is beyond the scope of the IB, but there isn't. What happens is the hydrogen adsorbs onto the platinum, and so does the ethene, and things happen. And no, there is no electrophilic addition here. So this is plain old simple reduction. Again, the actual mechanism is beyond the IB. Next up, hydrogen chloride. Well, I know I've got oxidation states of -2, -2, just like before. That's -3. Chlorine in the compound's -1, probably. H plus is +1, +1. So that's going to be -1. So let's have a look. The oxidation state of the carbon has gone from -2 to -1 and to -3. That doesn't seem to be consistent reduction. Have I gained hydrogen yet? Lost oxygen? No. Not looking so good there, is it? It is actually electrophilic addition. So where's the electrophile? Well, take a look at the hydrogen chloride. Oh, I've got to remember, sound more peppy. Starting to sound miserable about this again. Where's the electrophile on the hydrogen chloride? Chlorine has a higher electronegativity than hydrogen. So that molecule is polarized. And there we go. There's the positive part of the molecule. That's going to act as the electrophile. Moving on to hydronium ion being added to the ethene there. So I've got -2, -2. Oxidation state is -3. +1's hydrogen. -2 is oxygen. So that's going to be -1 for carbon again, is it? So I'm going to go from -2 to -3 and -1. That doesn't feel very satisfying. I've gained hydrogen. I haven't lost oxygen. I've gained oxygen. So it's all kind of gone a bit wrong. I don't think that's the case. This definitely looks like an electrophile, doesn't it? Something that loves electrons. Yeah, it's positive. So there's your electrophile there. So that's electrophilic addition. Again, it's attracted to these electrons, this high density electron rich area in the ethene. Moving on to the old chlorine here, to chlorinate it, -2, -2, that's going to give me -1, -1, -2 to -1, that's not reduction, it's not going down, it's going up, that's wrong. Gain of hydrogen, no. Loss of oxygen, no. That's not looking very convincing. So how can this be an electrophile? Well, where's the positive part that's going to be attracted to this negative area here? Well, these electrons are going to repel the electrons in this neutral chlorine molecule, and it's going to push the electrons away down that end, leaving this end a little bit positive. And here's your electrophile. Chlorine can be an electrophile there, slightly positive. Whew. And we're done. And the answer to the joke, snowballs.